it. You can just type these in as I'm typing them. So these are 3 hypothetical populations of leopards from which we sampled 4 leopards each. And now we want to look at whether there's variation between these 3 sites or not. So I'm just going to annotate this so that it does not get sites. Right. So now, whenever you have to do something in R which requires a lot of steps, it's generally hard to keep track of what you've done, what you've not done. So what I generally do is I first note down on a piece of paper what all needs to be done, and then I go around writing the code for it. Otherwise, you'll get somewhere halfway writing the code and then you'll realize, oh, there was this variable which I needed, but I don't have right now. So I'll just annotate here what all steps we need to do. So one, if we look at what all do we need? We need first SSB, sum of squares between groups, and SSW, sum of squares within groups. So sum of squares between groups, sum of squares within groups. Yeah. So I'll do the between groups first. So what do we need to do sum of squares between groups? I mean, obviously, when you're writing it down on paper, you write down in further detail. So for sum of squares between groups, first we'll have to make a list of all of the data points together. They can't be separate, right? So I'll make a length all, in which I do concatenate L1, L2, and L3. So this gives us one vector which has all of our data points. Oh no, I haven't run those, sorry. Yeah, one vector which gives us all of the data points. Now, next step would be to calculate deviations from mean, correct? So let's say SSL all. I'm just going to reuse the same object here and overwrite it because apart from preserving the basic, it doesn't matter too much. So deviations from mean, first we calculate the deviation from mean. So L all minus mean of L all. Okay. The next step would be to square this. So SSL all and SSL all to the power. So how you square things is you have this little cap arrow, which on my keyboard is on 6 that would be to the power 2. So just so you know, all of this could have been done in the same code. Like R allows you to like sort of, how would I call it? Not subset exactly, but yeah, put smaller, bigger and bigger bubbles. So for example, if I did this, then this turns into an object which is the deviation of means, and I can do to the power 2 directly to that. I don't have to do it in two sentences or 2 lines of code. Just so you know, I'm not doing it right now, just so that everything stays clear, but you can sort of bracket it endlessly as long as you can keep track of what is happening to which object. Okay. So now we have the squares for all of these, and in order to get the sum of squares all we have to do is sum of squares. Oh, I hope the object names are not getting too confusing. So now we have the sum of squares for all of the objects, like the global mean. So that is the SSB, we have it. Next step is to do this for each one of our subsets. So we start with, like we did there, yeah, this is L1, P, L1 minus P of L1. So just for practice, I will do the, sorry. This gives us the sum of squares for the first group. So let's see. Second. So actually, wait, I'll just do this one at a time. When you do this, you get the variation from the mean for all of them. Then when you do the square, all it has done is, sorry, all it has done is given you the squares of the deviations from the mean. And once you do sum, you will get a single number, which is the sum of our square deviations. That's 131 for the first population of leopards. Now we can repeat this for the second and third population. Just copy paste the code as this, and you can just change value names. I mean, it's confusing here. Just to demonstrate that all of this, like endless subsetting, is possible in R, I'm doing this for, I can just do the sum also in the same line. Sorry. But like I said, if you're doing this, make sure number of opening and closing of brackets is the same, and you have the right things are happening to the right object. So now we have the sum of squares for these second site, and next we have, I'll just do this for the third site. Okay. So now we have our four objects in which we have the sum of squares for each population or each sample, the total sum of squares between sites. So just to get SSW, if we add up all three of these, L1 plus SSL2 plus sum of squares of L3, we have our sum of squares within sites. And to calculate the F statistic, yeah, F stat. Okay, so also, sorry, in order to understand what exactly is happening, I chose this set of numbers. So let's also just take a look at what our means are like. So this is the mean for the first site data set. This is for the second. And this is for the third. 1 second. Okay. So the means are pretty much the same. And what is the mean for all? It is, yeah, obviously somewhere between those three. So here, what will happen if we calculate the F statistic? So what would be the F statistic? Sum of squares between sides. So this is all here. Divided by number of categories, if you remember the formula I showed there, which is 3 minus 1. I'm just going to bracket this so that there's no confusion in the code. That divided by the sum of squares within group divided by n, which in our case there are 4 data points in each one of these, so that would be 12 minus the number of groups that we have, which is 3. So now if we take a look at our F statistic, it's really high. I'm sorry, something has gone wrong here. Let's see. 1 second, there is something has gone wrong here because this is obviously too high. The sum of squares of the difference between, as we saw earlier, the difference between the means is what? We have 109 minus 110. Oh, I'm sorry. It's because what we had to do here was, okay, I made a mistake in the explaining. So what we have to do is calculate the sum of squares all for each subgroup separately. I'm sorry. That will be L1 all. So because there are 4 data points, we will do 4 into what? We have to do mean minus global mean. So mean of L1 minus mean of L all. Okay. And this we have to do 3 times SSL2. So this 4 that we're multiplying it by is because, remember, we have to do this for each sample separately. So for the first one here, 103, we have to multiply minus the mean of the group it is in from the global mean. For 105, we have to do this again. And since the mean of the group is not changing, what we're doing is just calculating the difference in the means and multiplying it by 4. So we have to do this for each one of these separately. Mean of L2 minus mean of L all. I'm just gonna remove this because it was all wrong. I'm sorry.
This is what the script is for, because
yes.
And make changes.
Yeah, I mean, if I had been doing this in the console, then instead of just making these few minor changes, I would have had to like rerun almost everything. Now I can just, and also for ease, you can just copy paste this and change the numbers because they're all the same thing. So I'm just leaving the object names similar. I mean, leaving similar object names so we know what's happening. Okay, so now we have it for all 3 groups now. 2 of the groups. Now we have it for all 3 groups. Now, just to make sure everything's fine, I'm going to
So now we're running just the object to see what it looks like.
Yeah.
And we're expecting a single value for these objects. The sum of squares should be a sum, should be a single value. If you end up with a bunch of numbers, then you're wrong. It's definitely not doing
exactly. So just to like check that nothing has gone wrong, you can keep checking at various steps of the running, especially when you're running very long pieces of code, because in the end, like when we did, suddenly you have something wrong and you're like, okay, I'm not sure where I went wrong. So it's best to like keep checking every once in a while. So now that we have this, now we need to square it and add it. So I'll try to just sum of squares between. I'm just gonna put it in the same code, so brackets, so that all the objects are separate. Sum of squares of the first one, all the part 2 plus sum of squares, variance from the global mean of L2 to the part 2 plus variance from global mean of L3 to the power. Now we have, it hasn't says, oh, there's no double L there. Now we should have SSB, and if I take a look at it, it seems reasonable considering all of our means seemed to be pretty close. One would not expect too much variation there. And you can just also run in each bit individually by selecting just that and doing control enter, sorry. And this is the squares that has been added to give us sum of squares between groups. Okay, now we do it again, and we take a look at our statistic, and what we find is still pretty high. Oh no, because I renamed it, sorry. SSD. Okay, yeah. So now if you take a look at it, it's 0.0300715. And this was when our means were pretty close together. In fact, I believe the only mean which was slightly different, the first one, which was about 109 point something instead of being 110. And everything else was 110. So what this is basically kind of telling us, because the numerator here is the sum of squares between means and the denominator is sum of squares within means, that most of the variation that we've observed in this data set is within means. And the sum of squares between means, so the variation between the means is actually quite low. Now let's just apply this to a slightly modified data set. So what I'm going to do is, again, make 3 objects, L1, L2, and L3, with 4 data points each, but the data points have been modified. So as you can see, what we've done here is increased the differences a little bit. If you would like to, once you got the entire data, you can try it out on your own and see if you get correct F statistic.
Just to make sure we understand this, this is really just to recreate the equation that we put on the slide.
Yeah.
R will calculate this for you when we run the tests.
Which we will do in like after this exercise. So this is just to also get some more practice coding in R. And as you can see, when you have long, cumbersome chains of code, making mistakes is very easy. Yeah.
I'm not sure what I did, but I'm getting an F stat of infinity.
Then switch. I think it's because, is SSB in the numerator or denominator?
SSB is the numerator, isn't it?
Yeah, I mean, infinity means your denominator is 0 somehow.
So my SSB is at 52. What is yours?
52.
Oh, because my SSW is at 0. Why is it 0? That sounds correct, right? It shouldn't be 0. What do you have?
What do I have? My SSW is 399. Wait, that's also too high, is it?
Not necessarily.
Okay.
And we can do it. I can do it check what it should be like.
Yeah. 1 second, just SS1 is 100. Yeah, yes. 155. Makes sense. Okay. Now we do the same thing for this bit of code. Now the convenient part here is, because we've maintained the object names for the input, and that's what the rest of the code is based on. All I need to do is just input the new data set and just run the whole thing from here. No changes required. So what is SSV this time? It's 924. It's much higher. Let's take a look. Why could that be? Because mean of L1 is 103, mean of L2 is 106, and mean of L3 is 113. So as you can see, the means vary much more than they did the last time. So when you square the variations from the global mean, this is what we're getting. So, and what is the global mean? Is 107. It seems a bit high. 23. Okay, yeah, I guess so. If you square 23, 5, and 18, yeah, you would get a pretty high number. So we're all okay here. Now we calculate the SSW. Again, no need to change anything, just rerun that code from above. and calculate the F statistic. And this time it's 49.2426, which is much higher than what we had earlier. So obviously, as we mentioned earlier, as with the t-test, what we can do to check whether this is a significantly different answer or not is look at the critical value table. But since we don't have access to a critical value table right now, and we're on R, we can just run ANOVA on R and see what R tells us. Yeah. So for that, first and foremost, we need to bring all of this into one data frame. So, and tell R that these are from 3 different groups. So in order to do that, what I will do is create a category variable, which will just concatenate. I'm just going to call them A, B, and C. So there's a difference.
So yeah, just to, while you're doing this, just to clarify that with so you can look at the help file for the function. We're just allowed to use a function basically to run an ANOVA. We hopefully see that the F value matches what we calculated manually, essentially.
If it doesn't, then we'll have to go back and troubleshoot.
It doesn't really, because I mean, it's a long equation to do manually, of course.
Yeah.
So you have to be careful, and doing it live is not easy, but I think it looks reasonable. Maybe it's correct.
I guess.
Yeah, just to explain that, yeah, if you look at the help file later for the function that we are about to use to run the ANOVA, it will tell you what it expects as an input. So for example, you can't just put the 3 groups one after the other, because it will not recognize it. It is expecting one column with values and one column with your grouping variable. So this is what Anne is creating right now. Is the column which is the grouping variable.
So if the function we're going to use is AOV, that's ANOVA, because in R there is a function called ANOVA, but that the input is something else. It's not just your raw data. We're not going to cover that today. So we'll be using the AOV. So if you look at here, what it's asking for is a formula, and data is equal to null, because there's no default there. You have to tell it what data set you're using. So we haven't covered formulas, have we, Guillaume?
We saw formulas when we did a box plot, and we saw
also
when we did the Bartlett.
Yeah. So it's basically the same thing. Like we want to calculate something as a dependent of something else. So in the box plot, you were like X as it relates to Y, and for ANOVA, what you would have to tell it is what is your response variable and what is your predictor variable, which both need to come from the same data set. So which is what we're doing here. We're creating a data set with response variables and predictor variables. Actually, let's just call this the treatment, and then we have to make.
I think you want it 4 times every time, not 3.
No, okay, correct. Thanks.
You can actually use a function for this. I can put it in the chat. You can
put it in the chat. Yeah.
So here we're doing it manually, of course. If your data set was a lot larger than 4 data points for each group, you might want to use a function instead of putting 4 times A and then 4 times B. I mean, we're just trying to create that data frame, and there are various ways of doing that. This is definitely, this is one way you can do it.
Yeah. So now for creating our response vector, what we will do is concatenate our 3 dependent variables. That's L1, L2, and L3. So now that we have these 2, just to check if we got it all under control, I'll do. So this, if you remember, dimensions gives you. Oops. Oh, maybe it's a there's no dimension. Dimension usually works for a matrix or data frame. So length.
Yeah.
Because this is just a vector. Length of response is also 12. So this works. So because if these were not equal in length, then we would have got errors when we tried to put them together. So now I will make a vector length. It should be a data frame. So that's just a data frame, and then populate this with our two vectors. So what I want them to be in two separate columns. So what I will do is cbind. So R will put each vector I put into the function now as a column, cbind, and just to make sure that nothing else goes wrong, the first column should be a factor, treatment, and the second column should be a number. So as dot integer, I think you can use as dot numeric also, but they will both serve our purpose. As dot integer. Okay. So now check that nothing went wrong. We'll take a look at it.
So I just want to say one thing. The first line, the as data frame, is pointless because you are overriding length with the cbind.
Oh, I am. Okay.
Yeah,
I just wanted, I thought that might be the case, but also I told that treatment was a factor. Why has it given it factor levels instead of just
because with cbind, this is now creating a matrix. So what you want actually is to put as data frame
before cbind.
Yeah, and then close this whole thing as data frame so that it turns that matrix into a data frame.
Okay.
But because it's going to create a matrix first, I think you might lose this factor thing.
Okay, which honestly doesn't matter because the purpose of it was just to make sure that the different treatments got treated differently, whether it's A, B, or C, or 1, 2, and 3, doesn't really matter to us because
yeah, it will be fine. R will recognize that the treatment column should be
a factor. Yeah, it's not going to treat it as a number. So
factor or a character. Even if it's character, it's fine. Like it will be able to.
Ah, that's true. Anyway, so now this is done. So like if you check class of length, what we have is a matrix, which is not what the input here is, because if you look at the arguments given in the help documentation, it says a data frame in which the variables are specified. Variables specified in the formula can be found. So it cannot be a matrix. So we'll just convert length to a data frame. As dot data dot frame length. There we have it. So now we will do AOV on this. Okay. So we will first assign AOV to an object. I will explain that why. Then AOV formula. So what do we want? What are the columns called? Oh, they're just called 1 and 2. We'll just change the column names as well.
Give them names. No, look at length actually. You haven't looked at it. What you're looking at is the. So
No, it's just V1, V2. So just for
column names also, just put column names.
Yeah, I'm just doing that. Okay. So we will just name the columns, column names of length should be as dot character concatenate, and we give it the two names treatment. So you can name it whatever you want here, just for ease of understanding the output, we'll call it treatment and response. Yeah. So now we want to look at the response that will be on the x-axis as a function, so tilde of the treatment. Data is equal to our length. Sorry. Yeah, length object. Okay. So now I assigned it to an object is if I just run UV, this is what I get. So it gives me the treatment and like some estimates from the calculation, but it does not give me the F value or the P value associated with it. So to get that, what you need to do is do summary of the AOV object. And here we have it. F value is different.
It is different. Doesn't matter.
But it's statistically significant.
Okay.
But also it shouldn't be, let's see.
So I guess we won't put, like, in the code that we'll send you at the end, we won't put the code that we put up there. But yeah, for your own, if you want to practice, calculate, like just using R and making, you know, using these basic commands, do try to calculate the F value manually and try to compare with this summary. And they should match technically. If they don't match, we can look into it. You can ask in the group what may have gone wrong.
Yeah, so just for one practice session, but also like because we didn't run a successful one, this is 3.
Has anyone tried actually and managed to get the same value?
Right, yeah, just mention it in the comments. I'm just gonna split this just in case that's where we went wrong. And then you add it.
So if there's anything like unclear, like in the code, because I know a lot of you are here because you want to learn R. So if there's anything that's unclear, don't hesitate to ask. We are all beginners, so don't be afraid to ask questions about the coding part as well.
Yeah.
Okay.
Not seeing a mistake here.
I think it's fine. Let's just move on because we can easily spend an hour trying to troubleshoot.
Yeah.
It's just
Okay,
it's a
because
long
the next
equation
step
and it's very
Yeah.
No
So
worries.
which is why the whole part of writing down on a paper so you can cross check, did I do this step before or after this step, is important, which we have not done right now. So when a code does not work, like going through it line by line, checking that the output is correct for each line, that is how you figure out whether what you've done, like where the mistake in the code was. That process is called debugging. So just so you know. Okay, so now what we're going to do is we will run a practice ANOVA on a given data set. Okay, so before we start that, just want to give like one overview of ANOVA itself. So in an ANOVA, like remember the null hypothesis, for example, in the t-test was whether depending on the type of t-test you're running, is whether the sample mean is equal to the hypothesized population mean, or whether the two sample means belong to the same population. If the two sample means are equal. In a one-way ANOVA, our hypothesis would be that, for example, right now we have 3 levels, so that all 3 means are equal. And the alternate hypothesis is just that at least one population mean is different from the rest. Now, like the assumptions in an ANOVA are pretty much similar to the ones that you mentioned for a t-test. So the one assumption is that the population for which we're calculating, comparing the means, are all normally distributed. But to be honest, ANOVA is pretty robust against this violation of the normal distribution assumption. Although if it's too far from it, it's not recommended. You can try other non-parametric methods. And the next assumption is that the measurement is interval or ratio. So for example, temperature, but basically continuous variables. You do not use ANOVA for count data, for instance, which is a discrete variable. Then there's the assumption that the categories are independent. Okay, so for example, if right now in the hypothetical test that we did, the 3 categories were 3 separate populations from 3 different localities. So these categories are independent. But for instance, if you have any reason to assume that, okay, for example, let's say you sampled in an open grassland habitat and a forested habitat and further divided those into under canopy, understory and upper canopy versus open versus closed in the grassland. These would not be independent categories because the understory and canopy is subsetted within the forested habitat. So that would not be recommended that you run a one-way ANOVA for it. Then we have that the samples are independent. So there is assumption that the samples have been sampled randomly. Like Guillaume said, one way a sample might not be independent is if you sample the same creature twice. Another way, for example, it may not be independent is if you just went out there and fought a bunch of families of leopards or, and measured all of them. Here, the samples are not independent because although you're measuring different individuals, these individuals being genetically related is sort of creating a small correlation there. So your sample size won't actually be the number of animals you sampled. It will be somewhere between the number of animals versus the number of families you sampled. And just don't allow me to confuse you based on this, but basically sampling should be totally random. And then of course there's the assumption of homogeneity of variance. This is that the variances of all of your populations are equal. Now, this is now because we're analyzing variance, and as you know, must have noticed, the variances aren't necessarily equal, but it's again sort of understood that it's fine if your sample size is equal, or at least not too drastically different from each other. So ideally, like most ANOVAs that people run is in what they call a balanced data set. So the sample size within each subgroup is equal. And there are modifications available if the subgroupings are not equal. But again, it shouldn't be like you have 5 samples for one site and 100 for another. There's no way ANOVA would give you a reasonable result in that scenario. Yeah. So now we will try to run ANOVA on a built-in data set. So as we mentioned earlier, R has a bunch of built-in data sets that you can use. The data set we will use is called plant growth. And this is how you load it. So if you just do data plant growth, it has loaded this data set plant growth as the object plant growth. So I can take a, if I do structure, str is for structure of plant growth. So it gives me this. So this data, it's a data frame with 30 observations of 2 variables. The first variable is numeric and the second one is a factor with 3 levels. And what if you want to look at what are the 3 levels, you can just do levels of plant growth dollar group. So the 3 levels are control, treatment 1 and treatment 2. So what this data set is, the numeric value is the value of growth of plants under 2 treatment conditions and a control. So I will pause here for like some 5 minutes, and we'd like you guys to try running an ANOVA on this, and then we will run it together and we can help you troubleshoot if there's any issues.
Also to clarify one thing is this data function will only work with built-in data sets. You cannot load data like that usually. It's only because that data set is within R already.
Yeah.
So don't try to load the UNCIA data set, for example, using data. It will not work.
Yeah.
Yeah, I guess 5-10 minutes, I guess.
Yeah, so we'll gather in 10 minutes. Guillaume and I will be here. We can help you troubleshoot if you're having any issues at all.
Yeah, just ask questions on the chat, or you can unmute yourself also.
Yeah.
I will also go to the bathroom real quick.
Okay.
Wait, should we share the screen still, or because they don't have the code right now?
Oh, right. Sorry. Okay, I'll just do that.
But so yeah, it's the AOV function that you want to use for this. Anything left, the part that is left of the tilde is your response. That's your numeric variable. The grouping variable is right of the tilde, and of course you need to specify which data set you're using, which then should be plant growth. All right.
So if you have any issues with any part of the code, you can just ask on the chat, or again, we're on a break, so you can just unmute yourself and ask. Okay, you got FSO equal to 0.059. This is for the plant growth data set. Okay, like, yeah, I haven't run it yet. We'll just run it and check if it's right. Yeah, it doesn't matter. Chi-square test is, it's sort of for count data. So even if you have more variables, it's fine. It's like a proportions test. Wait, actually, let me think about it. Chi-square.
What's the question?
Nothing. Chi-square, can it be run on if you have more than 2 variables? I said yes, but now I'm having doubts.
No, you can.
Yeah.
It's just like basically chi-square test is just account for different categories that you have, and I don't think there's a limit on the number of categories.
On the number of categories, right? Yeah.
And it's essentially it's kind of it's similar in a way. Of ANOVA, it's just like your response is basically another categorical variable. So it kind of looks like how many times do you have both categories together? It's like this table. I don't know. If I, for example, look at the categories male and female, like sex and location for the data set we're using, it kind of counts like, okay, how many females in that location, how many males in that location, how many. So you basically end up with a table. And with the chi-square test, you would essentially test whether
they're significantly different or not. So for instance, if you
expectation, if you expect, yeah, sorry, go ahead. Oh. Okay, I think Anne froze. But yeah, so you may expect, for example, both locations have the same number of males and females. Of course, you can look at the table, like you can count them. And of course, it will look like, okay, maybe they do, but they won't have exactly the same number. And so it's similar. It's the chi-square test will test for this. How much does it deviate from that expectation? It will not be 50-50 exactly every time. But the same thing, it's a statistical test that allows you to test, you know, how much difference do you need before you say it's a significant difference? So I think Anne lost her connection. Oh, she's back. We will not do chi-square test. Chi-square test is basically a non-parametric test, actually. And we will not cover non-parametric test here. So here we're really covering the basics of, and of course, that's why we're doing parametric tests only parametric tests. But the reasoning behind it is the same. So, which is why if you know how to implement a t-test or an ANOVA or whatever, the reasoning is the same. You will end up with a statistic. So the chi-square value in the case of the chi-square test. And again, you will compare it to a critical value and you have a p-value. So the reasoning is exactly the same. But of course, if you want to know how to use them and in which cases, you will have to look into it, of course. And the general setup is similar as Aliena said, the same. So you have to, for this kind of tests, because then you have Bayesian statistics, which is even more different because this is a very, we won't get into that for sure. But so yeah, for this kind of test, where even so parametric or non-parametric, you have to set your alpha level, like what is going to be your threshold for deciding whether to reject or not a null hypothesis. There will be a null hypothesis, there will be alternative hypothesis, or even several alternative hypotheses.
Basically what we're covering, all of this parametric, non-parametric tests that we're talking about are what comes under frequentist statistics. And there, how it works is you make an assumption about what the population should look like, or what the mean of the population should be, or what the distribution should be, or what a particular statistic should be, based on your assumptions of what the underlying structure is, and then calculate it for the sample and test it against your expectation to see if, like, how likely is it that your assumptions were right.
Yeah.
So generally speaking, you can, if your, the assumptions of normality or homogeneity of means is not meeting the standard expectation, you can really just Google it, like if you look for non-parametric ANOVA, you will find it, and you will find enough documentation online as well to help you sort of figure out. And also, this is just general purpose, like R help. So R does have a pretty active community. Like most programming languages will have spaces where you can make queries. So if you're getting stuck somewhere, number one, if you're getting an error message, what you can do is just Google the error message, and you can most likely fix the problem just doing that, because it will tell you what is causing that error. If even that's not working, then there are multiple websites. So there's one called Stack Overflow. Another one I can't remember.
I guess we'll just give a list at the end, maybe, for like resources. There's a few places that you will, even if you just Google, you will end up going on these websites anyway. That's where the community is talking, and we'll give you websites.
So most common issues will already probably be troubleshooted on these websites. But I would recommend that you thoroughly search that your problem has not already been answered there, because they can be pretty mean if you repeat questions. But in case it's something so specific that the answer doesn't already exist, you can always post questions and people will answer, and you get your responses relatively quickly as well. Help section in R, you mean the R troubleshooting community? So that's what, are you talking about the help section here in the environment, or the on the online thing? So if it's the online thing, I also don't use the R help section there. I think the layout is really confusing. Stack Overflow is a better option for that.
But the help file, you mean, like the documentation?
That's what I'm not sure. Are you talking about the help file, or like the R help in R Studio?
Oh yeah, but I guess there is this help tab, right? So
this one.
Yeah, so you need to use that, you need to call the help, right? You need to so the help will usually be for particular functions from particular packages, or from the base R, so the functions that come with R when you download it. So remember, that's the question mark. When you put question mark and the name of the function, you will have the help for that function. It's essentially describing to you what the function is and how to use it. And this is written by people, of course. They develop these.
Also, if it's a function that's not available in base R, then you have to put double question mark. Then it will give you like this list where there are similar sounding function names and the package that it belongs to. If you look up the documentation for the package, which will be available online, you should be able to get a similar looking file where it tells you what the function does. And if it's a package that is loaded on your system, then it will open the documentation by itself. But if it's not, then you have to go through.
What I wanted to say is that depending on who wrote the package and the functions, you will have help or not. Sometimes you have notes in the help file. Sometimes they will tell, like, and also even the error messages you get are from when people wrote this function. So sometimes you get an error that is very unhelpful. It doesn't tell you anything about it. Sometimes they will tell you like, oh, you have used a categorical variable and not a numeric, so you know what you did wrong in this case. So yeah, you see, for example, what Anne is sharing the screen. You have details. So the details of not every function will have details or even notes. So here it really tells you some information. I don't know if in this one particular, so here it tells you, okay, the formula can specify multiple responses. Cool. And yeah, and of course, if it's still not clear with the help file, then again, you can, the questions you have probably will have been asked already by someone on the internet. You will probably find the answer. Yeah, I don't think I ever had a problem with R, and I didn't find someone who asked the question before, and plus 10 people answering in different ways.
Yeah, but also another thing, when you ask for help in one of these forums, is to make sure that you're very specific with what your problem is. You can't be like, so someone should be able to not know your data set, read your question, and still be able to at least mimic what you're doing in order to be able to troubleshoot what's going wrong. So it's best if you can give details on what the data structure looks like and what exactly you already tried. So you'll get used to it or get an idea of how it works once you start looking for help in these places. Okay. And also, I think it's been 10 minutes now. Is everybody back? Give me your mute if you're saying something.
Oh, I am saying something. Does someone want to tell the answer? And and we'll go through the ANOVA.
Yeah. So Elena already gave an answer. Elena got F is equal to 0.0159. Did everybody get this, or did people get different answers from that?
Okay, we get different answers.
Oh, we got different answers. Okay. F is equal to 4. Yeah. All right, let's
run it. Try. F equals 0.0159 looks very small. Are you sure? Is that the p-value, or is that really the F value? Yeah, okay. I think that was the p-value. Yeah, okay.
Okay.
That makes sense. I mean, you can definitely get an F value that is very small. So that makes more sense. So again, for practice, if you want, try to apply the equation that is on the slide to practice kind of like using, just creating objects and putting everything together in one equation, and see if you get that same F value. So I'll just mute myself now so Anne can do.
Yeah, that's okay. I'm just running so this is the function. Guillaume usually uses head. This is just, I think different people have different preferences. So just to make sure that I have the names right, if you do names and the name of the object, it'll just give you a list of all the column names that are there in the object. So I'm using that to just make sure that, because if there's any differences in capitalization, etc., it just won't give an answer there. Data is equal
to inspect your data, there's a few functions you can use. As remember the structure function, STR. You can get names, so you get the column names at least. You can get summary. The summary function is pretty good too. It kind of summarizes all the columns you have in your data set. What else? There's head. You can type head and the name of your data set. It will give you the first few instances, so the first few rows, so that you don't have to look at the entire data set to kind of get an idea of what it looks like.
Yeah. Okay. So I guess everybody got it right, because the F value is 4.846 and P value is 0.0159. So that means it is statistically significant. So that means we get to reject our null hypothesis, which was that control is equal to treatment 1 is equal to treatment 2. But now, all that the alternate hypothesis states is that one of these means is not different, or at least one of these means is not different. So now how do we figure out what was different, right? This is where the second step of ANOVA comes into the picture, which is ad hoc analysis, which just means like after it, what you did. Post hoc, sorry, correct. No, correct. You're right. Post hoc analysis. Post hoc analysis. So for this particular one, what we'll do is, because we have three means and we want to compare them to each other, we'll just do a t-test and look at which means are similar. So I'm just going to create an object called significance table, in which I will assign the p-values. So first we do t.test. Oh no, first we'll have to subset these things because we need to look at how each one of them fares, right? So first we have the control.
Actually, shall we look at the box plot also to get, we didn't visualize the data here.
Oh no, that's true, we didn't.
This is something you should really do, like to, even before doing an analysis, it's a good idea to, we need to test the assumptions also, which we haven't done, of course, but to validate if we have any conclusion. You can do it before, you can also do it after.
Yeah. So box plot, that.
And it's the same, it will be the same as the same formula that we use for the ANOVA.
And just copy paste it.
Okay, so Priya is post hoc done only when we reject the null hypothesis? Yes, because in the case of ANOVA, if we found a significant difference, we don't know, like maybe two groups are there, maybe all three groups are very different from one another, maybe only two of them. We just know that some of these groups are different from one another, but there's three groups, we don't know which ones.
Yeah. So if the null hypothesis is not rejected, then that's it. Your test, all three means are equal to each other. Now there's no need to test which ones are actually different. So this is what the box plot looks like. And one second, I actually cannot see the bottom because of this share screen tab.
So they look actually all three quite different. The variant, like the spread of the data, at least. We're not looking again at the variance with the box plot, but it looks reasonable. So the homogeneity of variance is probably okay. We could test it, remember, with with that.
So actually, we can also just to look at, no, that's a tricky test. Okay, never mind. So, okay, they do look different. So I feel like maybe control and treatment 1 may not be significant necessarily, but definitely control and treatment 2, and these two most likely. So let's just do our tests. So I'm going to just assign t-test to a random variable, and you'll see why I'm doing that. T-test. Oh no, because before that we have to subset the groups, no? So, control subset. So if you remember, subset function is subset the object plant growth by the column plant growth group based on. So if it is, I also want the levels, just so we get our levels is levels plant growth dollar group. So now it has given us what each level is. So I'm just going to copy paste from here to avoid errors. So if plant growth dollar group is equal to control, take all of those rows and subset it in the object control. Then treatment 1 and treatment 2. Do the same things for this. Subset.
I guess we're making our lives easier just by creating separate objects. So
Sorry. I'm gonna copy this much so that Yep. So now we got it. Now we will run the t-test, and we just have to say compare control to TRT1. Wait, what? Okay, that worked. So basically it was expecting X and Y to be two numeric vectors, but I gave it two small data frames and it didn't know what to do with it, because part of it is, what do you call it, factors. So that obviously cannot run a t-test. So
It's
now
because, in the subset, you could actually specify you want only the weight.
only the
If you put $, if you put plant growth $weight, then it will return only the weight. Otherwise, it will return the entire data frame.
Yeah.
But subset it will just the number of rows.
Correct. So if I do $NDAT, which is where I save the t-test, it gives us the confidence interval, t-value, degrees of freedom, and p-value, which is 0.2504, which is actually not very significant. Now,
Not at all.
yeah, not very. If I do STR of NDAT, it kind of gives me what all factors or objects, like parts of the result is there. So you have the statistic, the parameter, the p-value, confidence interval, all of these, which is what we saw earlier. So you'll see why I'm doing this in a bit, but basically I'm just going to make a little table of all our significant values. So what I'm going to do is NDAT $, as you can see, the p-value, I'm going to just save it to an object here. Okay. And I did this just to make sure that what is the p-value called. So if I look at the significance table, it will just give us the p-value for that first test. Now we will do the same thing for the other two groups. So control with treatment 2 and save it again to our significance test table, concatenate. So
Okay, sorry about that. I think it's monsoon season in Kerala, so Anne has glitchy internet sometimes. I guess, okay, wait, I guess I'll just take this time to answer how was it Aliana's question? Just make sure that the two vectors you're using have, I guess, for some reason, there's not much data in there. So just check these objects. So you created an object called CRTL, an object called CRT1, and just look at them, make sure that these are vectors of numbers, because that's what the t-test function is expecting. And maybe when you created these objects, something different happened from what you were expecting. Maybe there's a single value somehow. So this is how I would go about it. Just inspect the objects that you're using as inputs to make sure they are what you think they are.
okay, I'm back. And Alina, I hope it's working. Just create the objects again. Make sure that the subsetting is working. Okay, so if you just click on it and do that, you should be able to see, like, there should be 10 observations in each object, because this was a balanced data set. Okay, so now we have our little significance table with 3 significance values, out of which just a visual inspection shows us that first one's not significant, second one is pretty borderline, and then third one looks fairly significant. So that's the comparison between this control and treatment 1, and this is treatment 1. Sorry, control and treatment 1, to control and treatment 2, and this is control treatment 1 and treatment 2. So now we come to one problem, like how you mentioned, we have our significance value set at 0.05, but 0.05 you could still be wrong, right? There's this 5% chance that you have rejected the null hypothesis when you release it. Just randomly your mean turned out to be that far away, but it's not really that far away. And this is a problem when you do multiple comparisons like this. So which is why ANOVA, you do the ANOVA first, because it's comparing everything together. But so let's say, for example, like let's take an extreme example, and we compared 100 randomly.
Oops. Let's just wait a couple of seconds. Aliana, did you manage to troubleshoot this? Is it working now? All right, perfect. Nice. Just wait a second for Anne to come back. Anyone else has questions at this point? Oh, we're back.
Sorry, I don't know why it's being so glitchy today. Till what point did you hear me?
I guess you can explain again why we're doing this.
Yeah?
Yeah.
Till what point did you hear me?
Yeah, basically you were saying that, yeah, there's this 5% chance that.
Yeah, that you will find 5%, you lost me at 5% chance, is it?
Okay, I think I'll just go ahead and explain what we're about to do. So basically, as we said, when we do a test, there's this probability that we are going to commit a type 1 error, remember? So we essentially, with this post-hoc analysis, sorry, and I'm just going ahead and explaining it because it keeps.
Yeah, I figured.
But tell me if I'm explaining it wrong. So essentially, when we do a test, there is a chance that we're going to commit a type 1 error. So of course, the t value that or the whatever test statistic that we're going to calculate may be very extreme, and there's going to be a p-value associated with it, right? The thing is that, yes, there is that chance that that value is very extreme, but not because there's a difference, just by chance there is this chance, which actually, if we set the alpha level at 5%, at 0.05, the kind of chance to commit a type 1 error is 5%, which is low, which is why we choose that threshold, because it is a low chance. But if you repeat t-test after t-test, of course, that likelihood is multiplied. So from a very low likelihood of committing a type 1 error, now you have a pretty high risk of that one of these t-tests is going to be just the outcome of chance. So in general, in statistics, when you do that, when we do several tests like this, which we are doing for the ANOVA to try to identify pairwise differences in means, we need to adjust the p-value. We need to be a bit more strict on the p-value because we know we have a higher chance. So essentially, this is what we talked about when we avoid the type 1 error. This is exactly what it is. We are adjusting the alpha level to reduce the likelihood of committing that error. Simply because we know by doing what we're doing, we already know we are increasing the chance of committing a type 1 error.
If you do a certain number of tests, 5% chance of committing a type 1 error basically turns into a certainty, right? Like if you have 100 comparisons, then yeah, probably 5 out of those comparisons are just by chance turning out to be significant. And yeah, Rohit asked, can you use Tukey and Fishers? Yes, I mean, technically post hoc, you can use any test that you deem appropriate. And we'll do an Tukey test in coming slides. Okay, so first, so now in order to restrict this chance or correct for it, we do what are called corrections. So one of the most popular ones is called Bonferroni correction, and that is just, I'll just, yeah. Oh no. Okay, that is basically your alpha value that you want to set it at. So in our case, the alpha. I'll just
share my screen so that I think people will see.
Yeah. I mean, I just wanted to show that one equation, so it's fine. So it's alpha value divided by the number of comparisons that you made. So M here is the number of comparisons that you made or the number of hypotheses you're testing, and alpha is, if you want it to be 0.05, that is what you'll set alpha as, or if you want it to be 0.01, like we discussed earlier, you want the alpha to be. And then you have another method also that I'll cover, which is the home method or the home Bonferroni, which is much less conservative than Bonferroni correction. So actually, as you can imagine, like Bonferroni correction, alpha by M, let's say you made 10 comparisons, then your this level of significance you expect to see is suddenly become 0.005, and if you increase it even more, it's going to keep diminishing to a point where it might be pretty unreasonable for you to expect too many. You might miss a lot of significant results because of that. So if you have way too many comparisons, people generally use the home method. So I'll describe both of them. Like, this equation is way more complicated than it looks. You'll understand it when I demonstrate it. So share. Okay, so what we will do is, first we will try the Bonferroni method. So I'm just going to use numbers because honestly our data set isn't that big that we need to assign. What I can assign alpha to an object as 0.05, M as, in this situation we carried out 3 comparisons, so that's 3, and basically look at divide by M. So that, yeah, so that our new level of significance should be, according to the Bonferroni correction, 0.01. So anything above 0.01 has to be rejected because of our repeated comparison. So if we look at that, 0.01, right?
Yeah.
Okay, so by that, this control and treatment 1 difference, no, this is control and treatment 2 gets this thing. So the only difference is between treatment 2 and treatment 1, which is interesting because so then there's no difference from control technically. So we will then now, I mean, of course, I'm not very familiar with this data set. It's a built-in R data set, but like it depends on your study system and your data, because you will know your data best to see if this makes sense to you or not. I mean, I guess if you look at this, yeah, there isn't that much difference. The median is kind of close to the control median, and these two are further apart. But let's try the home method and see if that helps. So now this is why I saved all of our significance values to a table, because the home method is a 2-step process. So first you have to sort your significance in ascending order. I think the default is correct. Yeah. So you sort your significant values starting from the one with the lowest significance, moving on to one with the highest significance. And then you pretty much apply a similar this thing. So for the first one, what you would do is alpha should be equal to or lower than alpha divided by the total number of comparisons that you made, which is 0.01. So in our situation, the first one is significant. If this one wasn't significant, then the test ends here. That means nothing else following is going to considered significant. But we found that the first one is significant. So then the next one we will compare to alpha divided by m minus 1. So you reduce the what you're dividing alpha by. So the level of significance for the next most significant value is set not at alpha by 1, but alpha by m minus 1. Which in our scenario is 2. So, it should be 0.025. So actually, this is not significant even with the Holmes test. So our conclusion is that if this were a study we were conducting, that there is no significant difference from control, but the two treatments did vary from each other.
So really appreciate that, we were basically about to, if we believe these corrections to be the right thing to do, we were basically about to commit a type 1 error. We were about to say, oh, there is a difference. Actually, there is not. And this is, that's what might happen when here the p-value is so close to 0.05. There is no way you can make a hard conclusion on this. It's so close to your alpha level, you at least, you first have to consider what you're doing and what are the chances of committing a type 1 error. And in our case, because we are doing several tests, we have to adjust a bit. We have to be a bit more strict. And even if you do keep that level, you need to at least talk about it in your discussion if you write a paper or even a report.
Yeah. Right. We'll clean up this code and send it to you. It is a little all over the place. Okay, so now I hope you got how and why we carry out the corrections. So I personally do prefer the Holmes correction because I have done analysis in which I had multiple comparisons, and even things that were 0.001 significant were getting dismissed with Bonferroni. Holmes gives you a little bit more flexibility there. Now we move to two-way ANOVA. So what do you do? Let's say if you have two factors, right? For example, in the UNCR data set, we have location, Altai versus Lacan, and we have sex for all the leopards, so males versus females. So if you want to look at the differences caused by this and the interaction thereof, let's say I just compared males and females to each other, or Altai and Bakan to each other, there is some level loss of information here because there might be a difference between males and females or a difference between Altai and Bakan, which you might just miss if you do these two-way comparisons. So use the two-way ANOVA where we can subset this into multiple factors. And here we will use the two keys test as the post-hoc analysis. So another advantage of a two-way ANOVA is that it will also give you sort of a prediction or a result on whether the interaction of the factors is influencing the data, or whether just one factor or the other is influencing. So in two-way ANOVA, again, the null hypothesis is that there is no difference between the means. Then there are three levels to the alternate hypothesis. One is that factor 1 has an influence. 2 is that factor 2 has an influence. And third hypothesis is that the interaction of factor 1 and factor 2 has an influence. So when you run a two-way ANOVA, your results will give you a separate F value and corresponding significance for all three, for factor 1, factor 2, as well as the interaction term between the two. So we'll try to run the two-way ANOVA on our data set. So we'll run it on BCI. So I'm just going to take the previous session and quickly do the BCI calculation. You don't need the plot.
You just run the whole thing, I think. Just you can select end everything, just run.
Yeah. So you only up to here, no? You don't.
Yeah. I mean, yeah.
Like the first hashtag didn't get, it got selected. Fine. Okay. I mean, we didn't need the box plots and all, but now we have our UNCR data set. So if I look at names, UNCR, we have all of it. Location, sex, length, date, and
yeah, last time we had logged the value. I forgot. Oh yeah, to calculate them. Last time we did the log them to calculate.
Yeah, sorry. So we'll use BCI2 for this analysis. And again, we'll use the AOV function. So just to make sure we have that here. We have it, our arguments and formula that we need to use. So again, I will assign it to model AOV. We want to look at both of these. So our response variable is BCI underscore 2 as it relates to. So for this, for a two-way ANOVA, what you have to do is our two response variables are sex, and then so for different types of, in the formula, the star usually indicates that you suspect there's an interaction here. It's an interaction term. But for a two-way ANOVA, if you just put sex interaction location, it will calculate the interaction as well as the separate influence of the variables. And data.
Just to be clear on that, if you just put a plus, like sex plus location, it will look at the effect of sex, so male or female. So it will look at whether there is a difference in BCI between males and females. If you put plus location, so this would be a one-way ANOVA. We put a second factor here, a second grouping variable location, because bleppers both have a sex and they also are from a location. So now you're looking at this factor as well. Okay, is location having an effect? So is the mean BCI different between the two locations? So that's a two-way ANOVA, and you have the chance to also look at whether they interact. That means, is the difference between males and female dependent on the location? Maybe there is a difference between males and females, but maybe that difference is not the same at both locations. So maybe the BCI between males and female is only a little different at one location and it's very different at another location. So if you don't put the interaction, it will just calculate the average effect of sex. With the interaction, you can say whether there is such an effect, an interaction. So like the effect of one grouping variable is kind of dependent on the other one, if that makes sense.
Okay, so let's just run this and see, and then we will look for summary. And here we go. And it looks like it is pretty significantly different for all of our factors. So this is what the results is suggesting. We have our F value, that's the P value. The P value of the influence of sex on BCI, the P value of the influence of location on BCI, and the P value of the interaction, which it seems there is one, but it's relatively smaller compared to the size here, because these two are very significantly different. That's E minus 0.07 is like, that's how many decimal points. It's just shrunk it to visualization. Okay, so now, which ones of these, right? Like we know sex has an influence, location has an influence, and the interaction has an influence, but maybe it's not, all of them. It's not like, do we know that it's the males and females at both locations are different, or maybe it's just one of the sexes at one of the locations? Like might be a slight variation. So again, we go to our post hoc analysis, and now we try the Tukey test. So the Tukey is called the Tukey honestly significant difference test, Tukey HSD, and this is a test which sort of gives you significance for all of the comparisons together. So we don't have to bother with the corrections for this test. The test itself is accounting for that when it's giving you the significance value. So I will THST, just in case I want to use this again.
We could look at a box plot maybe also.
Oh, correct, sir.
Always remember to inspect your data. It's always useful. And the formulation is exactly the same as the, I don't think you can put an interaction though.
That's what I was thinking. Can you?
I don't think you can. I'm just trying now, but no, you can't. It's it just ignores it. So you can of course just look at the BCI for the four, like, there'll be basically 4 boxes. That means there'll be one for females of altai, one for males of altai, and so on.
So since I can't put an interaction, I'm putting a plus. Yeah. So actually, it looks like from our box plot, the males at Altai are not necessarily different from the females at Vakan. These two are similar, but the males at Vakan and females of Altai are varying quite significantly.
Yeah, so it's in the
Again,
best body condition is males at Wakan have the base body condition. And then the males of Altai have the same body condition as females of Vakan. And yeah, so you can see that overall, if you look at the first and the third box, this is like for females, right? From both locations. So you can see that on average, the body condition of males seems to be a bit higher based on our measure.
And also the difference between the body condition of the female and males at Vakan is much lesser than the females and males at Altai. Like, so that's essentially where the significance in the interaction term is coming from.
Yeah, the difference is not the same, exactly. So there seems to be an interaction. That, I mean, we saw the interaction is not really strong, as you can see. So in the summary, maybe we should spend a bit more time explaining what the summary is, right?
This summary?
Yeah, so we have, so in the summary, we have each of our parameters, so like each of our variables. So we have, of course, sex, location, and then we have the interaction term, which is the third row. It gives you the residuals here also. It gives you, so of course, we have 3 tests here, right? We have one for sex, one for location, and one for the interaction. We have an F value associated with all of them. You can see the F value, the F statistic is very high for both sex and location. So it seems pretty clear, as long as we didn't violate any assumption, it seems pretty clear that we have, that BCI is different depending on sex. It is also different depending on location. And there's an interaction. The interaction, you'll notice, though, is kind of weak. It's not a very strong, it's not very strongly significant. It's less than 0.05. So if that's our alpha level, then it's still a significant difference. But we could say that it seems pretty weak.
So you can sort of tell that from the value of the F statistic as well, which is 4.8. So it's like pretty low compared to the F value for these two, which is 30 and 40. So if you remember, like, so in this, they're calculating each of the F values and P values separately for each subgrouping. So this is indicative of will be the sum of squares within that group versus the global differences in global sum of squares, like how we calculated initially. So that is implying that, so the ratio there is much smaller. So meaning that okay, let me be careful how I phrase this. The variation in the between group variations was not that much higher than the within group variations. Okay, and this is just a index for what is significant here. So now that we've looked at it, we will run the Tukey test and see what that tells us. For the syntax for that is, 1 second.
So the Tukey test, just to reiterate what we did, the Tukey test is doing the same that we did before when we did the t-test between each group. So when we did this pairwise t-test, it will just do this automatically. We kind of did it manually. We did one t-test, then another t-test, put all the p-values in one table to look at them together. That function, Tukey HSD, will do all of this. It will look at the ANOVA object, the two-way ANOVA object. So that's the first argument. Of course, we have to set a confidence level because R cannot guess that for us, but there might be a default value. So 0.95 might be the default, actually. We can check. So question, oh, it's not there. Is that from a library or?
No, it's not. 1 second.
I think it's a capital T. It's a big T.
Oh, right. Sorry, correct.
And I think the default is 0.95.
Yeah, must be.
So we don't actually have to put that here, but we want to be explicit. So maybe just for the clarity, we just repeated there. But yeah, you see, in the usage, there is already a value there. That's the default. By default, it will be 0.95, and we can change that to whatever we want.
Yeah. Okay, so we will run this, and if I just take a look at the object, this is the result of the Tukey test. So it gives us by divided by sex, location, and the interaction of sex and location. So this is just the, I think, the confidence intervals, the difference and the lower and upper limit. But what we need to look at is the value, which it has, as you can see, already adjusted for the multiple comparisons. And this is by each subgrouping compared to each other. And you have the p-adjusted value for all of those. So if you look at this test, I mean, again, like the ANOVA told us, it's pretty significantly different across the axis of sex, significantly different across the axis of location, as well as, so males in Altai versus females in Altai, very significant. Females in Bakan versus females in Altai, very significant. Males in Bakan versus females in Altai, again, very significant. And females in Bakan versus males in Altai is not that significant. In fact, it's not significant at all. So this particular pair.
That's what we saw actually, right? That's the box plots that were on the same level. And indeed, they're not significant. So just looking at the box plot, it was pretty obvious that they were not going to be significant. But now we have like a statistic, like a statistic, so like quantity to back us up, basically.
Yeah. And again, males Bakan versus males in Altai is relatively significant, and males in Bakan versus females in Bakan is also statistically significant. So this test is pretty much confirming what we sort of, eyeballed here with the box plot. But this is what you can then use to report your results. So there's another way to just visualize this. So if you plot the Tukey test itself, so since we have this as saved as an object, so you can just put this entire code in there, you'll get the same result. But since I saved it as an object, I'll just do this, and we get the distribution of it based on the, this is the confidence interval of each of these okay, so now it's not really clear how you can see. Like,
if you zoom, you might see the labels.
Yeah, no, but we can just make a small adjustment here. So as Guillaume has mentioned before, R does give you a lot of flexibility with generation of your graphs. So I'm just going to use this one. LAS is the code for how I want the labels to be oriented. And if you look for the documentation of plot, you will find it. And the code number 2 sort of makes it perpendicular to the axis. Now we have another problem where you still can't read it because the margins are too narrow, like no matter how much I open. So there's another code in R. So bar is a code that will allow you to set certain parameters for the plot, which will then just carry on till you turn it off. So right now what I'm doing is I'm just changing the margin distances. So wait, I'll just finish writing this, and there are certain default margins, just changing them a little bit. So it starts with the order goes from bottom to clockwise. So 4.1 is the margin at the bottom, 13, we're telling it to make the margin on the left-hand side much bigger. So once I've done that, I can run this again, and now we have our plot, which is readable. So yeah, so now we can take a look at this. Again, this is just a visual representation of what the Tukey test had already told us. Females in Bakan and males in Altai, the fact that this line is crossing this 0 border line is indicating that there is no difference between these two mains. And these are all the differences.
So just to read, I mean, I'm just repeating what you just said, but because this needs to sink in, like this is looking at the difference between the means. And in most cases, we know that this difference is is a true difference. So there is a difference in mean BCI. So of course, so we plot, that's the mean difference and the confidence interval, the 95% confidence interval. And we see that for one of them, it overlaps with 0. So we're not, the mean difference might be more than 0, it might be less than 0, but it might just be, it overlaps with 0. So clearly we can't say confidently that they are really different. Like here, it's pretty clear that, there's no difference between the two, statistically speaking. Like, of course, there is a difference, but it's so tiny that it's not, if you were to sample again, you would maybe find that, another way. If you were to sample the others, though, you would find this consistently if we trust our statistic here.
Yeah, and like these differences, for instance, the male Bakan and male Paltai, you can see like wasn't that significant. It's like pretty close to 0, but it's still falling on the other side of the line. So we can say statistically there was a difference. And Tukey test is adjusted for multiple comparisons. You don't have to do the Bonferroni corrections. Since we're on par as it is, I'll just cover like 1 or 2 more things, which is just one more thing technically, which is pretty useful. So par can be used to modify multiple factors. So par margin is equal to concatenate giving margin. You can change the margins. Then there is another one called MF row, which can help you change how many plots you can put within the same box. So right now, based on its par is set to 1 by 1. That's 1 row versus 1 column. So you get 1 plot per page. So let's say if I wanted to set it to this follows syntax as you would any matrix columns. So rows, then columns. So if I want to do 2 rows, 1 column, and do this. So the next time I generate a plot, it will. Wait, why didn't it generate the second plot? Oh, sorry. Yeah. Okay. So it will put both of my plots in the same.
That's actually quite nice. It looks nice, huh?
Yeah. Wait, it did something else. So.
Doing all
correct. Here it is. Oh, I think because this technically generates 3 plots. Sometimes. Yeah, now we have it. So now you have your box plot and your Tukey test plot on the same page. And
like what kind of stuff you can adjust with R. This is, you don't have to do this. It's just that,
Yeah, but it's just that, I don't know, MF row is something you use a lot. You might want many plots on the same page. So depending on what parameters you change, you can like populate more and more plots here. Just be careful about the readability. So once par has been set, it will stay like this for the rest of your session. You turn it off, or if you restart R, it will turn off automatically and go back to the defaults. So if you want to, before you turn off par, because it will shut down your plotting device completely, if you want to save your image files, you save them first. So you can just save as image, browse and select where you want to save it. By default, obviously it's into your working directory. Name the file, whatever you want, and it will be saved. Now to turn par off and reset to the defaults, you just do dev.off, or is it just dev off?
No, that's
dev.off. And nothing, just empty brackets. It'll close it.
Close down the graphical interface there.
Yeah, and now when you do it, it's back to the default. And yeah, that's how to do ANOVA, get your results, look at your results. And I think we're out of time now.
Yeah, no, that's quite a lot. We didn't manage to cover everything we wanted to cover. That's a lot. So for next week, we're going to start. So there's another data set that you will be using. I will, when I send you the code, I will write a line to load that data set you'll be working on. So it is the tooth growth data set, I think we want to use.
So like plant growth, capital T, capital G. It's a built-in package in R. So little bit homework for today. We want you to load the tooth growth data set and run a two-way ANOVA on it. And if you can, do the significance tests and test for normality and,
Yeah, so try to do all the steps, like look at your data, make sure the assumptions are met of your ANOVA, run the ANOVA, make a conclusion. So again, I will send you this code, and the last line in the code will be loading that data set. And you can just go from there.
And we'll just send you like an email on what all to do types. Not exactly what to do, but what we want, what the homework is. Yeah.
So then, yeah, and we will do it together when we meet again next week. Is that it, actually?
Yeah, it is for now.
Okay.
Does anyone have any, like, everything was clear, right?
We can stay online if you have questions, so we can address them. So maybe for like the next 10 minutes, we can stay online, answer any questions you may have. Next week, so remember, so to what we did today. So far, we kind of looked at, first session was descriptive statistics to kind of just describe the data you have. In the second session, we started looking into standard error and like trying to know where your true population mean is compared to the sample mean. We then looked at t-tests to compare two sample means, and we even looked at how this relates to population means, like how the confidence intervals may overlap or not. We then looked into ANOVA. So if we want to compare several groups, not just two, then we can use ANOVA. And of course, as you can see, for now, what we've done is we have a continuous predictor, sorry, a continuous response, and the predictor is the grouping variable was categorical, right? It's like you have either two groups or you have three groups. Next week, we're going to start looking into linear models, and linear regression involves a continuous predictor rather than a categorical predictor like reduce. So a very similar concept, actually. It's just that now the predictor is a continuous variable. So just so you know what to expect from next week, actually.
So Riaz has a question about when and how we should say the difference is significant. So yeah, I will use the example of what we did just now. So we did find that there was an influence of sex and there was an influence of location. And then when you broke it down into subgroups, there was no influence between the Altai females and the Wakhan males. So when you report something like this, like you can, of course, put in all of the significant values, but you have to look at what it is that you want to say. Like, is the lack of difference between the Wakhan females and Altai males, sorry, I'm confused, whichever order it was in, is it significant? I mean, is it important to the conclusions you're trying to draw or what you're trying to say? If it isn't, like, sure, you can mention that it wasn't significantly different, but for instance, in this particular scenario, we might want to focus on the fact that there was a difference based on the location and sex, and there seems to be an interaction because the difference isn't as much between the females and males of Wakhan as it is between the females and males of Altai. And if you want to say something about why you think that might be the reason. So what you choose to focus on totally depends on what you're trying to say. You don't necessarily have to.
That we found that there was no difference between the female of Altai and the males of Wakhan. No, sorry, females of Wakhan and males of.
No, I think it's the other way around. Females of Altai and males.
Yeah,
oh, correct. Sorry, females of Wakhan and males of Altai.
Anyway, this is a result, but I don't know if it's interesting. It's like, okay, they're the same, but so what? Like what the main question might be here, and of course, this is something you have to decide before doing the analysis. Like, what is the question you're trying to answer? Are males and females different in body condition? We know the answer is yes. Overall, there is a difference. And is the body conditions at the two different locations different? The answer is also yes, because we tested for that. And we also know that that difference between males and females is not the same as it is from one location to another. That's the interaction. So from what we did, there's these three conclusions. You could, of course, add, what was it? Females, the males of Altai as females of Wakhan. But there's no hypothesis behind it. This is probably not your part of your research question. So you don't have to talk about that one.
Yeah, I mean, for transparency, you could like put all your significant results or like levels of significance in the supplementary material or something, but it's not something you have to talk about, because otherwise in such large comparisons, you'll just end up listing your results. No one needs to know that. They just want to know, okay, what did you find? Why do you think it's relevant?
Right. It's like even just saying like, oh, the females of Altai have a different body conditions to the males of Wakan. It's like, okay, cool. But why is that your question? That's a result, of course, but maybe not the result you're interested in. Okay, so if you guys, I see quite a few are still online. So if you have any other questions. So if not, I guess we'll see you next week for some regression.
Yeah, thank you so much, Guillaume and Anne, for again a very stimulating session. And a reminder to you guys to see if you can bring your homework with you to next week's session. We look forward to seeing what you guys do with that.